So now we're going to look at what we mean by the standard electrode potential. Okay, the standard electrode potential, okay, standard electrode potential, also known as the standard reduction potential. We'll talk about why. Okay, standard electrode potential, also known as the standard reduction potential, okay, is defined as the voltage, okay, the voltage of a half cell, okay, or electrode, okay, the voltage of an electrode slash half cell, right, relative to the standard hydrogen electrode, relative to the standard hydrogen electrode. And this is measured at 298 Kelvin, 1 atmospheric pressure, using 1 mole per dm cube solutions. The symbol that we use for the standard electrode potential or the standard reduction potential is E naught. Okay. All right. So the standard electrode potential, okay, is a measure. It is a measure of the oxidizing strength of a substance. Okay, it is a measure of the oxidizing strength of a substance, right? Or the measure of their strength as oxidizing agents, right? So a more positive standard electrode potential or standard reduction potential means that the reactant is a stronger oxidizing agent, right? More positive E naught means that we have a stronger oxidizing agent. Okay. So we can say that the more positive the standard electrode potential, or more positive the standard reduction potential, right, the better an oxidizing agent the reactant is. Okay? The better an oxidizing agent the reactant is. So for example, right, let's say that I have the following half equations, right? I have copper 2 plus, gaining electrons to form copper. I have Zn2 plus, gaining electrons to form zinc, and then I have K plus, gaining an electron to form potassium. And the standard electrode potential for copper from the data booklet, okay, is positive 0.34 volts. Okay, the standard reduction potential for zinc, Zn2 plus, is negative 0.76 volts, and then the standard reduction potential for potassium, K plus, is negative 2.92 volts. Now these values are your standard electrode potentials. More specifically, they are standard reduction potentials. The reason we call them standard reduction potentials is because this data is always reported, right, for half equations where the electrons will be written on the left. Okay, so each of these half equations is showing reduction as the reaction, right? These are all reduction half equations, right? Electrons are on the left, right? You have oxidizing agents on the left hand side gaining electrons, right? And on the right you have reducing agents, right? So the backward reaction is the loss of electrons, right? That is, in the backward reactions, right, we have the reducing agents undergoing oxidation, right, losing electrons. So then looking at this data, right, which of these three can we say is the best oxidizing agent? We can say that copper 2 plus is the best oxidizing agent. Okay, copper 2 plus is the best oxidizing agent of the three. Okay, best oxidizing agent, right? So again, on the left hand side we have only oxidizing agents written here, right, because oxidizing agents undergo reduction. So we know that the reduction of copper 2 plus is the most favorable of the three ions. The reduction of copper 2 plus is the most favorable because it has the most positive standard electrode potential. Okay, so again, by convention, by definition, we always report standard electrode potential to standard reduction potentials. Okay, And based on that convention, we can say that since we have oxidizing agents on the left, the more positive or less negative the standard reduction potential, the better the oxidizing agent. Okay, so we can say this is the best oxidizing agent, this is the weakest or the worst oxidizing agent. Now the question is, which of these metals is the best reducing agent? So over here, right, if we were looking at which of these species present here is the best reducing agent, reducing agents undergo oxidation. So it could be copper, zinc, or potassium, and we know that potassium would be the best reducing agent. Okay, this is the best reducing agent, right? It undergoes oxidation the most readily. It undergoes oxidation the most readily, okay? So you're looking at the potential of the reverse reaction. So if you look at this for potassium, it would be plus 2.92 volts, right? For zinc, it would be plus 0.76, right? And the reverse reaction for copper would be negative 0.34 volts, right? Again, by convention, when we talk about standard reduction potentials, right, these values are shown for electrons being gained. So the negative of these values would be for the reverse reactions, okay? So we know that so here we can say that potassium will undergo oxidation most readily. It's the best reducing agent, okay? Because the oxidation of potassium has the most positive potential value or the least negative potential value. And here copper would be the weakest. Copper would be the weakest reducing agent. So again, when we talk about standard electrode or standard reduction potentials, okay, the way they're reported, on the left hand side you have oxidizing agents, and on the right hand side you have reducing agents.